Hello and welcome back to California Geology. Today I'm going to talk about some igneous shallow level and deeper level intrusions and also some chemistry on igneous rocks. So when we look over here, I want to discuss this volcano plutonic system. And I've already shown you this diagram, but I want to emphasize that an intrusion, which is essentially the magma chamber as the ascending magmas come up from the mantle into the crust, they're going to intrude into the country rock. So the country rock is the older pre-existing rock. Now this magma chamber over time will send smaller intrusions, kind of tabular intrusions that cut across pre-existing strata. Remember, these layers are the strata of older rock, country rock. And so the dike would cut across those. And we would say that a dike is a discordant tabular intrusion, discordant, because it cuts across those strata, those pre-existing layers. Now for the sill, note that the sill would be a tabular concordant intrusion. In other words, it conforms, or that intrusion takes advantage of a pre-existing weakness between sedimentary layers. And there we go, it's between these two strata right here. And then the magma chamber itself, that will eventually solidify into a solid rock. And when that magma chamber completely solidifies into rock, it becomes a word called pluton. So a pluton would be the solidified magma chamber. And these range anywhere from a few kilometers to tens of kilometers in diameter. Some of the Sierra Nevada plutons are up to 50 kilometers in diameter. So they're really large intrusives. In fact, in the Sierra Nevada, there's so many of these plutons, individual magma chambers that coalesced, that came together, kind of got stuck together, pasted together as they formed in a convergent plate boundary. And these many plutons together make up what's called a batholith. So batholith, so remember the Greek word bathos means deep. And lith is a Greek word for stone, so deep stone. So many plutons coming together, and they have to make an area of over 100 kilometer square area. And here on my PowerPoint, I have a little diagram showing a cross-section along Highway 80, and we see these individual plutons. These were all magma chambers that solidified, and together they make the Sierra Nevada batholith. And so recall that the batholith is being formed at an ocean to continent convergent margin, and we call that a magmatic arc. So that's what Sierra Nevada, it's a magmatic arc. It's the roots of a magmatic arc. And then the batholith, you see it's forming down here in that area. Now, looking over here at the composition. So we want to focus on the chemistry of igneous rocks. So for composition, this is an important chart that I have here. And what I'm showing that we have volcanic and plutonic rocks. And then we got the composition. We got felsic, which is going to be rich in silica. Mafic, which is rich in magnesium and iron. And then intermediate is somewhere between felsic and mafic rocks there. And then a category that I haven't talked about yet is called ultramafic, and these are very rich in magnesium and iron. And so the rock names you should understand, felsic volcanic rocks are called rhyolite. So rhyolite is a volcanic rock. Here in California, there's several rocks that are called dacite, lava domes, and volcanic flows that are dacite. Dacite is a felsic rock, but it's on its way to becoming andesite. So because we have a lot of dacite, for example, parts of Lassen Peak are dacite rather than rhyolite. And then for the plutonic equivalent of a felsic rock, that would be granite. Granite is higher in silica, has lighter colored minerals. Now, in California, our Sierra Nevada, the bulk of the granitic rocks in the Sierra is actually this rock called granodiorite. So it's still considered felsic, but it's on its way to becoming this intermediate rock called diorite. Now for the intermediate rocks, andesite would be for volcanic, and diorite is a plutonic. We've talked about basalt for the mafic rock. If basalt cools at depth, underground, it becomes a plutonic rock called gabbro. So these are equivalent in chemistry. And then we talked about peridotite because it's a mantle rock. But when Earth was hotter, back in an eon called the Archean, lavas of peridotite actually formed, and those were called komatiites. Those don't form anymore because Earth is not hot enough. But nonetheless, that's our our order there. So if we want to look at kind of the distribution of basalt, here would be a dark volcanic rock. So here we can see that this lava has the green olivine crystals in it. But then the andesite, you can see it's a little bit less dark. It's gray, and it has some of that hornblende instead of the olivine, hornblende and plagioclase. And then for the rhyolite, here we have a rhyolite volcanic rock, which is clearly lighter. In fact, if we zoom in a little bit on this rhyolite, I want to point out that there are some quartz crystals in here. In fact, I can see one from back here. So there's a nice quartz crystal. There's a nice one there, nice one there, nice one here. So this one definitely has quartz and also some potassium feldspars. There's some potassium feldspar crystals in here as well. And so looking at the compositions for these, in fact, before that, let's look at the granite. So here's granite, light colored. Granodiorite, here I have a large piece of granodiorite. You can see this granodiorite is a little bit darker than our granite there. And then the diorite, you can see we start to see more of those mafic minerals, And then finally the mafic rock would be the gabbro. So you can see that's definitely a darker rock, more mafic minerals. And then we've already seen the peridotite ultramafic rock. Now let's look at some of the minerals present in these different types of rocks. So for felsic rocks, quartz and potassium feldspar, biotite hornblende, perhaps. Usually I say there's plus or minus here of hornblende. For the andesites, plagioclase and hornblende. That's two of the main minerals we see in andesites or intermediate rocks. For mafic rocks, olivine and pyroxene. For the ultramafic rocks, certainly olivine and some pyroxene, right? So you can see how as we're going from felsic to mafic, we start going light colored, gray green, black green. So we start changing color here, right? When we think of the magnesium content, right? Magnesium and iron increases as you go toward the more mafic end, whereas silica increases as you're going toward the felsic end. Now, let's look at basalt. I always have a question about basalt. It's important for three reasons. The first one, it's found at mid-oceanic ridges, seafloor spreading. We talked about that already. And because it erupts at mid-oceanic ridges, it's the most voluminous rock on Earth's surface. 90% of all volcanic rock erupted is basalt, and primarily it's coming out of mid-oceanic ridges. And the seafloor covers most of our planet. About 70.8% of Earth is ocean floor. There you go, most abundant rock on planet Earth. Now, if we look at number 3, basalt has a key piece of evidence for seafloor spreading. In other words, there are minerals in basalt called magnetite that crystallize from the magma, and they act as tiny compass needles that record Earth's magnetic field in the past. And we can use those magnetic signatures to verify seafloor spreading and plate tectonic motions. Now, let's look at peridotite. Peridotite's important for 2 reasons. I always say it's important for 2 reasons. The first, well, we talked about it being the rock of the mantle. It's a rock of the upper mantle. And second, and most important for igneous rocks, is that magmas come from partially melting peridotite. So peridotite partially melts to produce mafic basaltic magmas. So here I have a couple points on the origin of magma. One of the first things I want you to know is that magmas don't come from the core. The core is too far away. It's 2,900 kilometers away. They come from the upper mantle, probably the asthenosphere or melting in that mantle peridotite lithosphere. And there's 2 ways of doing it. You either get something called a decompression melting or a hydrous flux melting. Now, here's a diagram showing a couple of important features. There's temperature on this x-axis, and pressure is going down on the y-axis here. What I want to point out is there's this line here called the dry solidus. In other words, these are conditions in the mantle where there's no water, where it's dry conditions, which are most places. And this other dashed line I've drawn here are conditions for when you put water in the mantle at subduction zones. Remember, when you have a subduction zone, that ocean lithosphere is hydrated, and when it gets down to about 100 kilometers, it's going to experience melting because of that water being released, and it's going to change conditions here. So one thing about this dry peridotite solidus, note that as you go deeper, you need more temperature to melt the rock. If you're to the right of this solidus, then you have a partial melt. You'll have magma. But if you're to the left of it, you have 100% solid rock. 100% solid rock. This other line here is the geothermal gradient. So as you go deeper in Earth, it gets hotter, right? So note that even deep down here, we're not hot enough to melt the rock. We're still in the area of 100% solid rock. So that's why the mantle is primarily solid, right? It's not magma. Now, so the reason we increase this line to more temperature as you go deeper is because you have more confining pressure. Confining pressure. So the deeper you go, more and more pressure inhibits that kinetic energy, that melting. It'll prevent magmas from forming because there's so much pressure. The magmas are hot, but if you can move them up toward the surface, well, that would be decompression melting. So at divergent boundaries, like mid-oceanic ridges, here, we're looking at maybe 30, 20 kilometers down. If we could somehow move that rock, and that's what happens, the rock moves up closer to the surface by seafloor spreading. The asthenosphere moves up at mid-oceanic ridges. You cross that peridotite solidus, and you get that decompression melting. So again, that's occurring at divergent margins and at hotspots like Hawaii. Now, at subduction zones, convergent margins, water is introduced into the mantle by that subducting ocean lithosphere. And around 100 kilometers down here, that water begins to leak out of that downgoing subducting lithosphere. And so that's going to change the conditions completely for this peridotite melting point. And so now we're going to focus on this wet peridotite solidus. So now anything to the left over here is 100% solid rock. But if you cross this line, you see partial melt. So here I have a rock at about 100 kilometers in a subduction zone. Because in a subduction zone we have the presence of water, you can see that we're in the region of partial melts and we're going to produce magma. So understand that the hydrous flux melting here, this is going to be in subduction zones. We'll put subduction here. Whereas this one is in divergent margins, right? And hotspots, we'll add that, hotspots. So that's the origin of magmas. They're coming from the upper mantle, and there's two ways. You're either going to have the decompression melting or this hydrous flux.